class to make sure everybody is here on time, but let's go ahead and start with the introduction. So I'm Tony. I'm one of the instructors. I'll be leading the this week's class, which is linked list, and then also much later on the dynamic programming and recursion stuff that we're doing in August. Just a little bit about me. I put it on the class, but I'm currently at Google. But before that, I spent about 11 years or so doing startups after my PhD, which was actually in neuroscience and electrical engineering. So kind of an atypical background, and but I've spent a lot of time doing interviews, both on both sides of the table. So I'm really happy to share what I've learned about that with you guys. So Iris, you're here too?
Hi, I am the other instructor this summer. So just to give you a quick intro, I'm teaching a few classes over the course of the summer, so I'll be seeing you guys throughout. And just as a quick history, I guess, I currently work as a software engineer at Pinterest. I've been there close to 4 years, and I've been there ever since I left school. So I've pretty experienced being like an interviewer. I also kind of remember what that process was like, doing like internship interviews and like new grad interviews. So yeah, it's nice to meet you all, and I'm kind of excited to work with you guys over the summer.
Do we have, is Karen here? Nope. Nathan? And any of the TAs?
I'm Reed. I'm a TA. Hi, nice to meet everybody. I'm Reed. I'm a product engineer at Ridgeline. We're a financial technology startup up in Lake Tahoe. I graduated about 2 years ago, so was very recently through a lot of interviews, and now I write our technical interview questions and run those up here. So really happy to help everybody out.
Awesome. Do we have another TA? I believe we have two more here today, if they have logged on already. Okay, well, I think that probably means that they'll show up for the breakout session. So that gives me a segue to describe how we will run these meetups that we have twice a week. So most of them are pretty much designed to have half the time us lecturing or giving details about a topic, while also then giving the other half, so a huge hour, to do the breakout rooms, which is practice time for all of you to work in groups. And that's when basically the TAs and some instructors and whoever's here will also be floating around the rooms to interact with you guys while you're going. And I'm going to explain a lot more about what those breakout rooms are like and why they're so important to this course and why we've designed it this way. So let's take a step back. This course, we've called it Advanced Interview Algorithms. And I think it's important to point out that this isn't meant to be an advanced algorithms course, in that we're not going to spend our time working on some minutia of fascinating algorithms, but really it's more about getting advanced at the algorithm process as is presented during a computer science interview or technical interview. And that's really it's its own thing. It's a special beast all its own. And so we've designed this course to help people get advanced at that process. And we like to think of it as really a game, because one, it keeps it lighthearted. That there's a lot of stress going into it, and we all want jobs and stuff like that. But in the end of the day, you do your best and you perform your best if you let that stress go, or just try to get to the point where you're having fun with it. And really, you are scoring points. So in the end of the day, whether we like it or not, technical companies have aligned themselves to develop this process that they believe is somewhat meritocratic in that anyone can come in, and if they are great to work with, and if you think they're going to be a solid engineer that you want to be sitting next to while you develop the next new thing, then this interview is supposed to help you as a microscope, to in a really short amount of time, because it's really hard to figure out if we like to work with each other, but in a really short amount of time, make some kind of a decision, thumbs up or thumbs down. And in the best processes of the best companies that do this really well, they've figured out some system where they can, judge certain parts of your performance, because that's what it really is. It's a performance together. We're acting out what it'd be like to work together. And that's what we've, all the instructors here and the TAs have, put our heads together over all our years of experience to describe the shortcut to working on that and practicing on the performance piece. And so to that, we've found a set of real common failures. So we'll be discussing those throughout the 12 weeks, as well as a sort of a happy path of, the most important bang for your buck way to study to do well in this performance. Because again, this isn't advanced algorithms. It's not just about knowing everything in computer science, which is impossible. It's too large. There's so much to know. But if you do know a lot about computer science, that's great. It is going to help you out because the algorithms in interviews are from computer science. But there is a subset of them that the interview process sort of migrates very slowly, but it focuses on a subset and it kind of changes that over time slowly. So it's important to have a somewhat up-to-date course like we have here. And we have went through a lot of trouble to break down to the exact problems that we thought if everyone did fantastic on them, then it would be a no-brainer that you would go in and nail an interview the next day. And so some of these common pitfalls that we like to bring up. So as we're saying, this is an algorithm interview. And the number one common pitfall that we see all the time, especially out of fresh graduates, is they believe it's a coding interview and it's not an algorithm interview. So as soon as they get a problem, they say, oh, you want to see my coding skills? So I need to do something with the linked list. So let me just start writing in Python right away. And they start coding it up. And maybe you're a great coder too, and you just hack it out right away. And you say, well, here it is. Here's my code, and it works. And a lot of times you actually will not proceed on from that interview. And people have asked, well, why is that? And it's because the algorithm process, you get a lot of points for communicating your thought process, being social, in that you are communicating to me, this other person, the other interviewer on the other side, what it is, how you're going about solving the problem, why you're thinking of it this way, et cetera. And that's actually really important, if not oftentimes more important than if you can just code, because people want to work together to solve problems. And the problems are often much harder than the ones you get in interviews. And so if we can't understand your thought process and we don't figure out if it's fun to work together, oftentimes they'll vie on the side of, well, I don't have enough signal to know if this is the right hire, so let's not move forward. So it's a lot about your thought process, and also about, yes, it is about being social. And that's something that as engineers, we don't have, perhaps a lot of us have already biased to the sides of not being super social, and that's why we chose to study science and do programming and spend all the hours we do building these cool things. And that's why the breakout room, so those number one and number two, being social and explaining your thought process, is one of the reasons why half of the course is devoted to us practicing that together, because it's a special type of communication to explain the algorithm as you're going through it, as you might feel frustrated, as you have aha moments, et cetera. And so you need to be practiced in that. And so that's one of the reasons the breakout room is super key. And one of the things we don't want is to jump to coding right away or to sit there in silence. So always be speaking. So in past classes, going around the rooms, one of the big faults is in the beginning, no one's kind of speaking, or they're just like, already drawing it up. So it's about speaking, whether or not you do know something or don't know something. If you don't know something, speak up and ask right away. And we're here to move this along and also to practice talking. So that being said, one of the other big failures is actually too slow. So now I just said you should spend all your time speaking, and I'm actually going to give, and throughout the whole 12-week course, we're actually going to give a lot of techniques to slow your process down so that you're not just coding. But the other one is you actually have to get fast at being slow. So you have to get fast at explaining yourself because you only have an hour. And so one of the reasons why you're practicing is you're going to get good at explaining the most important things that you need to explain, and just that, and continue to move on. So those are kind of the three major pitfalls we see, and that we believe we can help work on throughout these breakout sessions, as well as the homework. And again, in addition to these, the other sort of takeaway that we have for the course is practice. So we believe the interview is kind of like, the interview process is a lot like an interview muscle, and that you need to basically spend continuous time that you allot every week. Some of the best students sometimes figure out a strategy that's like 30 minutes a day. So they pre-block out a time in their calendar, whether or not you're on an internship right now, you're busy, but you can still fit in 30 minutes to just solve one problem every day. And try to keep it time capped also. So another common problem is that people that are actually motivated, they start off and do problems and say, okay, well, I'm going to do one problem every day, but I'm actually going to finish it. And I'm going to do it all by myself. I'm not going to ask for help. And they can just spend a lot of time doing it. And that's not what it's really about. You should spend a certain amount of time banging your head against the wall to try to get it right. But really, again, it's about moving on and just making sure every day you're putting in some work to get a problem done. So time cap how much time you're going to spend on it. And towards that, so we help out by, we've already created the LEET code and hacker ranks that you'll do every week that are actually mandatory. So those are the mandatory assignments. And we have basically a 3 strikes policy, which is meant to, just like a good physical trainer might give you, accountability to say that you're here to actually do the work. Otherwise, you don't need to participate in the class. So you have 3, unexcused absences. So if you, don't show up and there's no reason, and there's also just, and every assignment is mandatory. So was there any, and while this is going on, I see a lot of chat messages going through. So I just want to make sure if there's any questions about the way that the course is going to be run. And yes, all the sessions are going to be recorded. That was one of the questions. Videos are recorded. I believe they get released pretty soon after each lecture. Great. Okay, so let me just present for my slides right now. I don't want to share my calendar. There we go, desktop. Okay. Okay, so we've already gone through the introductions. Is there any TA that didn't introduce themselves that has now showed up and will be in the breakout rooms?
Hi, I'm Parul. I took the course last year. Sorry, I signed in late.
No problem. Great to see you, Photo. Did you want to mention something about yourself so that we can remember?
So I'm not sure what questions you guys are exchanging, but I just graduated from Brown University and I'll be joining Amazon for work in July.
Great. Perfect.
Hello, this is Yash. I attended the interview preparation course last summer, and I am a TA right now for this session, and I am currently interning at Cisco Attrition Analytics. Good to be working with you all.
Awesome. Nice to see you again. Okay. So algorithms are the key to the algorithm interview, and as I described before, it's not just about coding, and so that's why we have this process. Specifically, I mentioned that we've audited these interview questions. You could go out there and you should practice a lot of them on the side, but please pay attention to these ones first. We've specially curated them to address a specific breadth and depth exactly for the course that we're pretty sure if you can nail them, that 90% of the interviews you're going to walk in and get that bump or nail that interview. In addition to that, we believe there are a few key patterns to memorize, actually. So most of algorithms is not about memorization. It's about how you think. And it's okay if you don't know certain things. And a lot of times the interviewer will even say, oh, you don't remember that? Well, I think it's this. And that's fine. And it's more about like how you can work with that. But there are some things that if you haven't memorized it, you could end up doing something much harder, or it's very hard to derive on the spot. And they come up so often that it really pays to memorize it. And so we will point those things out and give you the time to memorize those few things that are necessary. In addition, each one of the topics has topic-specific strategies. So linked list, there are a few that you'll learn today, and so that's what the lecture is about, is kind of pointing to those, as well as the docs that we've prepared on the course webpage or GitHub page. And then the practice challenges at the end of the before the hacker rank, and then as well as the hacker rank itself, which we believe is our best attempt at saying, okay, now you have this pressure environment, now try out these tools that we've given you. So the weekly schedule is, we'll have a Tuesday lecture, I already mentioned, have its lecture, have a breakout. You should be doing your problems before the lecture, even if you can, to get some warm up with it. They're often easy problems first, just to get to touch the material. Then we'll move through the lecture. Oftentimes we'll do a problem live, and then we'll go to the breakout. And then Saturday is again a lecture and interaction session, and oftentimes that might be a deeper dive into a material. So the first 4 weeks are like this. There's 12. I just wanted to point out with the schedule, we have this review. So interspersed throughout the whole schedule, we have these review weeks that we basically give ourselves a chance. Say you were falling behind a little bit and you kind of didn't really understand this material. It's a great time then to double down, go back and even redo questions that you had done poorly, and redo them for yourselves to, again, focus on your weak spots and or catch up. And then if you are doing really well, the review gives you time to even make sure that you're even faster at understanding certain topics and patterns. Okay, so let's get to linked lists. I see a couple chat things have come up. Let me just look real quick. What are the homework problems? They're on the course portal page. Yep, and there is a link to it. Nice. Okay, so linked list patterns. So specifically, the linked list actually has just a few patterns. Linked list is sort of considered a somewhat straightforward topic of problems, but can be tricky if you're not comfortable with pointer manipulation, basically, or thinking about just keeping track of bookkeeping. There's a lot of little details, and so we have a few things that mostly are techniques that help you keep track of little details to build cleaner implementations. So some of those are multi-pass, which basically states a lot of times when you have a linked list problem, oftentimes computing some value before you write your algorithm can be very helpful, and it often doesn't change the order of magnitude of your complexity of what you're trying to solve. So for example, if you're already dealing with a linear time algorithm, you have to touch every node. Maybe you could just go ahead and compute the length if you need the length to do something. And so that's the basics of multipass. So this lecture isn't, by the way, I'm not going to explain all of these in detail. The site has the docs on all of these techniques. I'll just point them out. Two-pointer technique is something that you basically need to memorize. It's useful for a few specific kind of problems, but they seem to come up a lot, often dealing with cycle detection, so or things of that nature, whereby you might need a fast pointer iterating through your list and a slower one, and it just happens to be a trick that allows you to figure certain properties out about your linked list structure. Dummy head technique is a particular technique that is not often necessary, but ends up cleaning up a lot of edge cases. It's a style of programming also where you create an invariant, something that that should be upheld while you work through a problem. Reversing a part of the list, so that's both a problem that often comes up, which I'll go over quickly here in class, but it's also a sub-technique in that oftentimes knowing that you can reverse a single linked list often is a sub-part of other problems that are more complicated. And we'll discuss that more. And then linked list is also, although rarely done because a lot of people don't necessarily want to see this, but this does come up because recursion is sort of becoming a little more popular with functional languages becoming more popular again. And it's a great proving ground for asking you questions about recursion. It just happens to be one of the most basic sort of data patterns that veils itself to a recursive type of solution. And then sometimes you're asked to show certain sorting algorithms or other algorithms using linked list as a data set. But this is even more rare. So the two largest patterns that we'll really be talking about today, one is pointer bookkeeping, and this is about accounting. So it's just kind of like this fancy name of pointer bookkeeping. Really is just like use if you're familiar with programming debuggers where you can watch variables as you go along, it's just telling you, hey, draw yourself that visualization as you're trying to solve a linked list problem so that you can see what you're still pointing to. Diagram the memory, because that's what everybody, that's the only thing that really trips people up with linked lists is what are you still pointing to and can you solve the problem? And so this is kind of a technique to help you visualize that. And then umpire, which is our suggestion for how you should solve all algorithm problems, actually, which is a acronym that stands for understand, match, prototype, implement, review, and evaluate. And I'll describe what that means in the context of an actual problem in a little bit, but most of those letters you should know. Understand, meaning to understand the problem. Match, meaning to match it to tools that you know, like these strategies. So, I'm going to use this strategy. It seems like it'll apply, etc. Prototype is when you're drawing it out and maybe a little pseudocode. And implementation. So part of this, one of the main things you could take away from just umpire and why we even talk about it like this, is that code doesn't even come up until the fourth stage. So again, this is to really reinforce, because this is the biggest problem we see. Do not jump right into coding. Coding is something that's done later on. So you go through a lot of stages first. You look at the problem, you talk about it, you come up with some cool examples of what you think stresses the problem out or is a good example of what the problem should solve. Then you kind of write a little bit of a solution to it, and then you finally start coding. Review your coding, so that's when you go and debug your coding, assuming there are bugs in it, and evaluate the runtime, making sure you're always giving in the end your complexity analysis of your algorithm. So I'd like to demonstrate pointer bookkeeping with this sort of sort of intro problem of reversing a linked list. Now, I've already had several problems with my Zoom technology today, so let's see that I can, let's stop sharing. And now let's share this particular device. Whiteboard. Okay, that is not sharing. Okay, maybe if I put it on my screen. Okay, one more thing here. Maybe quick time. Okay, this is once again. Okay, I think what this is it works on Zoom when it's in the web app, and then it doesn't on my MacBook when I'm in the Zoom app, which I was forced to join because of this because I was joining a meeting. And I think that's what happened last year too. And that's why I had tested it and it worked. And then when I use it in class, it doesn't work. Okay, so I will have to fake it again with the drawing. And that is really unfortunate. So let me go to share my screen. Now I'll share this PowerPoint, and really it's part of what I had to do last year as well when the video also flaked on me. What is that? Are the okay, one second. Apparently I closed the browser that I was in a moment of panic through this. Okay. So now that I've wasted 10 minutes messing around with my camera, I'm kind of going to zoom through the reversed linked list, since it's kind of a simple problem, so that I can get to this other problem that I want to get to also and discuss with you guys. Unfortunately, I'm going to just have to talk through a pointer bookkeeping rather than drawing it out while I'm here. But let's see what we can do here. So let's present this. The idea is that, say we're given a problem. Actually, I can't present it because mode, and I can't do it. So say we're asked to do the following, reverse a linked list. We're given 1 connects to 2, connects to 3. And then you are told that the answer should be 3, actually points to 2, points to 1. What happens to a lot of people that are just on the border of being comfortable with this is they start, going off. Oftentimes they're the ones that, try to code this up first. They just right away say, oh, I kind of understand this. Let me go ahead and write Python. Let me call it reverse. And then they, take a node, which is part of the list, and then they just start typing like, well, current equals node, and then they just get lost somewhere. I've seen this so often, even though this is, they might have even solved it before. I've heard that too before, but then they get lost, and where they typically get lost is they weren't holding on to a piece of the list as they were going through it, and then their head kind of explodes as they try to think about where they went wrong. And so pointer bookkeeping is about, as you go through this problem. So you already see some of the marks here. Let me try to reverse what was done here to get us back. It's meant to be this debugger you're making as you're going along. So if we just try to imagine this as a whiteboard, and I'm just drawing this out as I'm going, but we have this list and we want to reverse it. And the things that you're going to often do is use a pointer to parts of the list because it's singly linked, so it's hard to get back. And you don't want to keep running over and over again, because that might lead to like a polynomial runtime or something like that. So you want to do it in linear time. And so as you walk through, you need to always be holding on to certain pieces of the list. And so one strategy is to, and again, this happens before you even know what the code is. So it's kind of this mix of intuition and just drawing what you think is going to happen. So you want to reverse it. and you start here, you always start at this end of the list, because if you start here, you always have to keep walking back because there's no pointer back to the rest of the list. So you want to keep this current pointer, and I call it the current, perhaps is pointing to the rest of the list that we haven't reversed yet. So it's nice to name these things so that they're invariant. So current is rest of list that we have yet to see is rest of list that needs reversing. And then, maybe I'll have an R too. I'll say, well, that's probably holding on to my reverse list. So that's a bit of a dummy head technique also, where R is already ahead to a new list. It's this reverse list. So I might start off in none. Okay, so then we start walking through and see what we can do. Okay, so if that points to the rest of the list. So say I assign 1. So now R should actually point to 1, we say. Bring that over there. And it points to 1. And then, well, current, okay, well, it should point to the rest of the list. Okay, so let's move current to the next. So you would draw this pointer to say, okay, well, current is now going to be over here, and it's no longer going to point to this guy. So we exit out. If I had drawn it, that's what it would be. And now it's there. Okay, but we need to keep reversing it because now R, this reversed list, it's not satisfying the invariant. It's pointing to 1, which then points to the rest of the list. So what R is now pointing to actually needs to point to none in this case, because 1 is the end of the reverse list, because the reverse list will be at the end 1. But really the sort of, as I already say that, I know, well, that only happens in the first case. And generally what happens is that what was C before now needs to point to what was R before. And, well, I've already just repointed R to 1, so I kind of lost what R was pointing to before. See, as soon as I pointed R can only point to one thing at a time. So that's why in pointer bookkeeping, I like to always suggest that you kind of have what it was before, you scratch it out, and then you move it to the next spot so that you can kind of see this trail, this history, this temporal history of C was here, but now it's here. And similarly, R, so it was there, so let's go ahead and scratch it out like I'm saying. So it was pointing to none before, so scratch that out, but now it's pointing to 1. And I realize, well, if I need to now make 1 point to none, I actually need a new variable because I don't have enough things holding on to those memory locations that I need to complete this step of reversing pieces of it and having the rest of the work to do still. So that's fine. So that's where you see I had that N coming up here. Let's move over here. So I'll have this, well, maybe in this case, it's like a T. It's like a temporary variable. T now is actually pointing to none. So what we do is, you go back in time. So you realize you made a mistake. So in this pointer bookkeeping, this is the way it works. And this will happen in interviews too. Maybe not with linked list, with reversing linked list, but maybe. That's why it's here to help you. You say, oh, I lost my memory here. So I still need another variable to hold on to it. So let me go ahead and reverse back. So say I didn't do this. So take this back, and I haven't connected it yet. Take this back. And what I do is I come up with another variable T, and before I do anything with R, I say T is equal to R. So T is wherever R is currently. So it's this temporary variable that holds on to what R is currently. Now I can go ahead and make my move where I point R to where C was. So I would have gone all the way back in time to where C was here. Now I've got R pointing that, so that makes me lose my pointer to where R was previously here. But that's okay, because T is now still pointing to R was. And now R is pointing to 1. I've moved C ahead to the rest of the list, which is 2, 3, 4, the rest of the list that will need to be reversed. And now I can go ahead and say what is currently R will now point to what R was previously pointing to. So what that means is that instead of pointing to 1 now, instead of pointing to 2, the rest of the list, I'm now creating a new connection, which 1 will now point to what T is pointing to, none. And now I don't really care about T because now I'm kind of back to square one again. I have a reversed list. R points to the reverse list, which is just a part of a list, R1 to the none. So this part of the reverse list. And C points to the rest of the work to do. C is current, so it's the current pointer to the rest of the work to do. And that's sort of the essentials of pointer bookkeeping that now has gotten me to a place. As soon as you basically use it to find the key loop, the key piece of the loop that you're trying to work on. And this code, so had this have not been here, but I'm just trying to use it to short circuit us through this sort of simple problem. Let's go ahead and erase this to look at the code. Oh, and you see I kind of solved it differently this time. So, so it shows you that, there's multiple ways to solve this problem. And in this case, before I was using a temporary variable to hold on to where C was. So you can move either one first. In this case, I'm using a temporary variable now to hold on to where the reverse list is pointing to. And so you see that what we basically decoded with this pointer bookkeeping is this inner loop. So in our case, we said n or t is actually equal to r dot next. It really doesn't matter which way you go about it. And then r, we said, will now, r dot next will now actually point to, R is going to point to C, etc. Move it through so that it then points to T and move along the list. So what pointer bookkeeping is? So again, I don't want to spend too much time on this sort of trivial problem. I kind of want to move on to the next one, but hopefully you see that it's meant to be a visualization, so it's a lot better when you can draw this and then slowly write this out to the point where you understand exactly. Okay, I can move my pointers to solve this problem in a visual way, such that I'm never losing track of the rest of the list. Okay, so are there any questions on this though? I don't want to move too fast. Scroll through the list and flip the pointers, if that makes sense. I don't understand that approach, so perhaps I'll try to jump in your room when we break out into the breakout room, and you can explain that to all of us that would be in your breakout room a little bit more when we get in there. But yeah, there are a lot of ways to solve it. Can we do pointer bookkeeping again on Saturday? Yes. In fact, pointer bookkeeping is going to be it's going to be a strategy that you should almost do for every linked list problem. And I have a video on it, and you can see solving the problems there. Yeah, that'd be nice to have paint. Yeah, so right, so 3-pointer. So that's what so what Young is mentioning here. That's how you see there are 3 pointers here. It's kind of the standard way. And another person's pointing out, yeah, don't try to turn this into a doubly linked list. Okay, so I only have a few minutes to move on to the next. And I want to kind of describe how to approach these problems as well. Again, umpire is kind of our key to solving all of the algorithm problems. It's our skeleton for how we're going to approach the problems. Understand, match, plan, implement, reflect and verify, and evaluate performance. In the last problem, I didn't really do that. I just kind of jumped into the visualization part, which would be the plan, because I just wanted to show the pointer bookkeeping technique. But here, let's take a look at this problem. Given a singly linked list, L, we are asked to reorder it such that if we have this list L0, L1, Ln minus 1, all the way to Ln, so we have n plus 1 nodes in it, we want it to basically look like this, where it's L0, then it's the last node. So first node, then last node, then second node, then second to last node. Okay. So that's interesting. So what understand means, oh, and then it of course gives us some things here, which is part of understanding. So you may not modify the values in the list nodes, only nodes itself may be changed. And they may not have even said that. So an interviewer might just start off with this question. And what understand means is it's a time to, you're immediately given a problem, and rather than even draw it, before you even start drawing it, it's important to talk about the problem. And so that's what we'll also be doing in the breakout, which is immediately say, okay, well, what does this mean? Does it mean in place? Does it mean, can I use extra data structure? So that's a very common first thing to ask, especially with other problems, linked lists. It's almost always, they want you to do most of it in place because that's part of the challenge of linked list. And so part of understand oftentimes means that you will 11's too small. You'll write out examples. Like that is one of the main things you should be doing. So say, okay, 1, 2, I like to write out my most common example first here. 1, 2, 3. That seems like a very easy example. So maybe we'll just add one more, 1, 2, 4. And so just to make sure, that should look like 1, 4, 2, 3, right? The interviewer says yes. And so then you can move on maybe to edge cases and say, well, what, the common edge cases for linked lists is a one node. So, well, if I only had one node, what would that be? Well, if, that would, you could return, can't do it, or you would look for a sub pattern. And often the interviewer would suggest the sub pattern, so we just return the node. Or the null, the empty set, so it was given none, so that'd be the empty list. Also want to return none. And so that's a great time to be talking to the interviewer, also be asking about complexity, desires from the interviewer, whether it's linear, logarithmic. Sometimes they won't tell you, they just say, do the best you can. Okay, great. So now we kind of understand the problem. Now we go into matching. So that's the understanding phase. Now in the matching phase, it's all about matching it to tools that we already know about. And in this one, and I kind of gave it away a little bit in solving reverse first, but it kind of looks like this has a reversed list in it. So in matching phase, I should be thinking, okay, there's probably a reverse linked list. Since I know how to do that, I might need to use that. And because I probably need to touch every node, and I need to reverse half of the list, I probably need to maybe get the length first. So if I had a function where I could get the length, and that's like a multi-pass, so that takes advantage of this idea of multi-pass, where it's a linear problem, so I have to touch every node. So it doesn't hurt to spend a linear amount of time first getting the length of the list so that then I know where I might need to split it. Because what it seems like is that this problem might be a lot easier if I just consider it the merging of two lists. So what I mean by that is, say I have 1, 2, 3, we'll just say, so now we'll take an odd length list. And what if I considered this the merging of the first half of the list with the reverse of the second half? So that means I'll consider the problem merging these two lists, 1, 2, to the list that's just the 3 node. Well, that, and now you can see, well, that's not that good of an example because that 1 is a degenerate case, just the 3 node. Okay, so let's add 4. And again, this is part of what understanding and matching is about, is finding a good case that you'll use as your like prototype case during the prototype example. And so really, it was nice to get a 2 length 1 in your second half at least, so that then you could see, okay, to the reverse one of this. And then another strategy that I don't think we really name in the course and talk about because it's a general programming strategy, but I like to call it magic function, or and then a magic function appears, partly just to like really make myself remember this very useful strategy. And what this means is that sometimes when you look at a problem, and this problem in particular can be solved, I think, very cleanly like this, is I kind of feel like I know the structure of it. So I kind of like to first solve it by not even showing pointer bookkeeping yet, but actually just saying, okay, suppose I had some magic function that given this list and the reverse, it just merged and then gave me what I wanted, which was this interleave list here. So I'll just call this the interleave merge. And I don't know how to do it yet. I'm just going to go ahead and write it down that it exists, and I'm just going to see what it does. So then if it did that, then my job, so I just sort of look at the components of what I need to write, and this is just sort of standard programming. Well, what other functions would I write? Well, first I want to get the length. So I'd want to say n is equal to, we want to know the length of the list, get length of node. Oftentimes the linked lists, you just have, the pointer to the first node. So oftentimes that's how you pass the list around. So get length of node. And then what other magic function do I want to exist? Okay, once I have the length of the load, the length of the list, I want to split the list in 2 based on node and n, the length. And then after I've split it, and I'll be using, so you already see this is kind of gone to pseudocode, but it's still at high enough level where it's really prototypey and I'm just naming things. So that's why it's not really code at this point. So I split the list into these 2 halves. Then I reverse the halves. So we'll call it R, rev B is equal to reverse B. And this one's nice because it exists because we just did reverse. So we know we can do that. Whoops. And so if we look at these sort of functional blocking that we've been doing, get length, then we split list, then we reverse, and then we interleave these. And as I said, since this just magically just merges them to provide you the answer, then as long as it does that, this actually solves the problem. So we've now come up with an algorithm that as long as we fill in what's inside of each one of these functions, the algorithm is solved. And that's it's a great way to fast forward to already say, this is my, this is kind of what I'm thinking, and talk to the interviewer about it. Again, that is sort of a method that is useful for problems that might have a lot of bookkeeping, like do this and then do that. Maybe you have to split the length, etc. And then you can go back and say, well, do I need to figure out how to solve this one? Get length. And oftentimes with get length, the interviewer knows, you know how to do this. So now you can start skipping pieces of the problem that you don't even have to solve. So that's why this technique is especially useful for these annoying kind of bookkeeping ones where you're going to have to draw a bunch of functions eventually, because you can immediately say, okay, well, yeah, we know how to do this. We know reverse, he's already tested you on in the beginning of the interview. By the way, this is often a way to do like a follow-up kind of question. So he first hits you with reverse, makes sure you can do that, and then says, okay, now what about this? split list, this is probably one where he will make you solve it, as well as interleave merge. And that's then where you would break. Now I can treat each one of these as a separate kind of umpire problem, although again, you want to speed up through it. So split list, I would then, and I can't really now do this visualization on here, but basically I would go ahead and do the pointer bookkeeping on this problem. So sorry, 1, 2, 3, 4. And your job is given n, which is the length of the list, and given the first node of the list, which is 1, you would just need to walk down n over 2. And this is the only tricky bit, which is just you're going to return 2 lists, and one of them, if it's odd, is going to be longer. And you'll have to think about which one it is, and then you'll decide, oh, it's the first one because you start first. And that's the only tricky bit about it. Again, using pointer bookkeeping, you'll realize you'll need a couple pointers to do this, both a temporary one, and you'll have one walking forward as you get to the half of the list. And then you'll basically cut off once you've walked. So you'll go from the current, which is 1, and then you'll send another pointer off to go 2. And then once it makes it to n over 2, you say, okay, this is sorry, you have to do n over 2 minus 1. So you have to be on this pointer. So that's, again, why pointer bookkeeping visualizing will help you out. You have to be here when you then sever the next, and you also keep track of it with a T to what this will be so that you don't lose it. And so as you sever, so basically anytime you're severing a connection, there's another pointer involved. That's the other way to also think about it. And pointer bookkeeping just really shows you that. So after you sever the connection, then you say, okay, well, T was pointing to this. So now I return these 2 lists. And then interleave merge is a little more interesting, but it's actually part of one of your the problems that you'll be doing. I think we even covered in the breakout session now. So I kind of wasted a lot of time futzing around with the camera again. So we're 5 minutes already into your breakout, but I think that leaves us with a good, I really wanted to make sure to cover this extra sort of strategy and then how we use it together to solve a meteor kind of problem. So let's go into the breakout rooms, and then I'll catch up with the chat and also jump into rooms with all the instructors and TAs. Yeah, 156 people here. Okay, so let me give a recap of what I witnessed in the breakout rooms, at least. So I could only attend a couple of them, actually, but I thought the people in the breakout rooms were working very well, working very hard. But a sort of common problem that I noticed was that the talking about it, and this is what we expected. We're not pros at it yet, and so I noticed 2 sides of it. And I want you to think about if this happened in your room or not, because I couldn't be in all the rooms, so I can't tell you what happened in every room. But both the rooms were full of very capable interviewees. Actually, you guys are all like clearly have been exposed to some problems before. That's great. But in all the problems, whether or not it was the person exposed, I could tell they were exposed to a lot of problems already, or the ones that maybe were exposed to less. Everybody was kind of zooming through the problem a little too fast, or not saying enough things that were convincing the other people that that the problem was actually solved. So the real 2 skills that we're trying to work on, I want to go all the way back to the beginning of the lecture. Yeah, there are these techniques that we're giving you: pointer bookkeeping, dummy head, remember reverse, etc. Those are pretty important, so remember those. But practice speaking what you're doing. So in this case, we had these quick questions. So the idea was to look at the question and then just start using pieces of umpire. So understand. So in one of them, I believe it was delete, nth to the last node or something, I think is one of the ones we're working on. So part of understanding is pointing out, well, here's some of the tricky cases that I think we're going to run into, and itemize them. And you can go ahead and work on your piece of paper. If you can't show, if you can't project like I was dealing with today, you can work on a piece of paper on your side and describe to them what you're doing. That does a number of things. One, it sometimes gives you the solution. So while you're just describing, you have to work at a certain level of detail. You can't work so high level that, you know, you're just hand waving so much that you won't really understand the problem enough to the point where you've actually got the algorithm. But if you start describing and say, well, if it only has 2, such and such will happen. Oh, but they also said that I'll always be guaranteed to. And then maybe you'll realize, well, I don't actually know how to solve it yet, but I know this really bad way. State the bad way. Tell everybody what the bad way is and describe actually the algorithm of the bad way. We had a case where that happened in one of the breakout rooms where as soon as he described, so he resisted saying anything. He was just kind of quiet there saying, well, I kind of don't know how to solve it. And we said, tell us the bad way that you don't want to tell us. And as you walk through the bad way, he realized what the solution was that he actually wanted to do. I think that was with the palindrome one. So all of the lessons for me of that was speaking, but also speaking at the right level. And then the other one was the amount of information you're given. So it has to be at the right level of detail, and it can't be too much information. You have to really cut it down to exactly what is the, you know, the exact pieces that are gonna solve to be the algorithm in the end. And that includes using the understand, trying to match it to previous tools you had, and then drawing that out for yourself and others. So this breakout room, we're gonna have a lot of practice with this. This is gonna be a common thing, and we're gonna go in the rooms and try to help with this. So let me look at the chat too. Can we do, can we get the quick question link? Oh, things are moving so fast. Can we get the quick questions links in LeetCode? Yeah, I believe each one of them should be a link to LeetCode. We can work on trying to give you the links that, the answer to the palindrome question. Well, I don't want to ruin it for other people that they are trying to solve it right now or work on it, but yes, I can give it to you privately, I guess, if you already want to know what the answer is. Find the middle. Okay, well, somebody is already giving it away. Next time I'll share my idea there. Pair coding, yes. So pair coding. So this one was meant to be sort of quick and more of the just really working on the talking part and visualizing it for yourself. But yeah, a lot of them will be doing collab edits for breakouts. And any other questions? Do interviewers prefer a well-explained solution over an efficient one? That's a really great question. I'm glad I scrolled all the way up. They want both, but you will win more points always by explaining things. So I've definitely experienced a really good solution to something that was someone that didn't get an offer at a place. And again, it's like I said, you have to give enough data points for people to say, this is someone that I want to work with. I think they're going to be good at all these other problems, and not just, oh, maybe they memorized that one or they already knew it. And, you know, that being said, like people work differently in different ways, and we all know that. And so, you know, it's a fuzzy process that we're using, but we're trying to, in this class, give you all the tools you can to make it so that you have that edge. You're able to talk about it. And I do think a well-explained problem is, one, sometimes it'll get you, like I just said, it will get you to the efficient solution. So it's both a way for you to gain points, and while you're gaining points, you might uncover the best way to solve the problem. And how would you flip? Okay, so that's all the way back there, and then no more new questions. Okay, great. So let's call this session a wrap. We'll meet again on Saturday. I will again go through some iteration of solving my video tech problems. And just make sure all of you, so some of you also had, different tech problems. You only had your phone or something like that. Try to make sure you show up, in class with audio, with video, and at least, even if you can't share what you're like, something for you to write on to work through problems. Collab Edit will also be used in a lot of the breakouts.
And Tony, do you recommend like memorizing all these techniques?
So we point out certain things for memorization. Linked list doesn't really have a lot of things for memorization because it doesn't avail itself to that really. But there are a few, like the 2-pointer thing. But what is there to memorize that except to use the two of the pointers? I definitely do not recommend memorizing answers to any problem. So that does not help. So don't try to, palindrome, let me memorize exactly what that algorithm was. Not useful. Too many problems, and then in the end you probably won't be able to describe it maybe well. It's better just to practice the approach of solving problems.
Thank you.
Okay, so yeah, see you on Saturday, and be doing your work up to Saturday. It'll definitely pay off.
Thank you.
Thank you.
Thank you a lot.
Thanks.
Thank you.
Thank you.
Thank
Big
you.
thank you.
Thank you.
Thank you.
Thank you.
Bye.